Okay, good afternoon and Happy New Year to all of us. Today, we are moving to the problem number 3 of our midterm examination. And on this problem, we're going to be able to determine the internal forces and moment in the structure. And I should call you back again to the basics of the analysis of the structure. We will start by the first step to the free body diagram of structure. This is going to be the beam. When you get the correct free body diagram, then you will use the equation of equilibrium to compute the reaction. So the problem shown over here is the free body diagram of the beam, and then we have the reaction. Then we will use the second step. Again, we're going to use the free body diagram of segment of the structure of the beam. Now, we cut the beam and then we set up the reference coordinate x1. Then we will use the equation summation of x sub x equal to 0, summation of f sub y equal to 0, summation of the moment equal to 0 to determine what? To determine the shear force V sub x1 and the moment M sub x1. Oh, it didn't change yet. Then, following this one, after you get the equation of the shear force and the moment, you will be able to draw the shear force diagram and the bending moment diagram. The method that we use called the method of section. We got to cut the section of the beam, of the structure, and then we determine the relationship of the shear force with the coordinate. Okay, so this is on this one. After you finish what you learn here, you should be able to draw the free body diagram, determine the reaction, and also draw the free body diagram of the segment of the beam, determine the function of the shear force and function of the bending moment. Now, we mainly design and use to resist both bending and transverse shear. So the main thing, when we plot the shear diagram and moment diagram, the ending result, we're looking for what's so-called the maximum shear force and maximum moment in order to determine the cross-section of the beam properly. Therefore, this one will link to the other subject called mechanics of material. In this subject, we only draw the shear and moment diagram based on shear and moment function. And the next course, we should be able to design the beam. Now, based on this one, you got to refer to the sign convention. The positive sign convention reference from the left to the right, from the left to the right, and the downward, we assume it to be positive. When you get the negative value, it's going to be upward. Okay, and then the positive bending moment will be this one and this one, and the positive bending moment how to bend the beam in the shape like this one, like you bend the ruler. This is for the positive moment, and this is for the negative moment. Now, the procedure of the analysis. Again, we will first draw the free body diagram and use equation of equilibrium to determine the reaction. And then after you get the beam reaction, you will draw the body diagram based on selected coordinate system. When you select the coordinate x1 and x2, just cut the section of that given coordinate x1, determine the equation v sub x1 and v sub x2, and then after you get the equation of the v sub x1, v sub x2, m sub x1, m sub x2, later you should be able to draw the shear diagram and moment diagram. Okay, this one you will have V max equal to plus minus 2.5 kilonewton, since the maximum positive here, maximum negative here, and then also we may determine the M max that's going to be at this point. And then we have an example, and I prefer to show you guys how to solve it based on the handwriting. Let me move you to this problem, okay? And then based on this problem is a kind of example for your midterm examination. When you get it, please try to read it properly. This beam is called simply supported beam. There are three types of beam in this study. One is simply supported beam, and this also may be called a simply supported beam. We also have this type of beam. This one called cantilevered beam. Okay, this is the second type. You should focus on this one. And also we have the third type. On the third type, we call this beam as the overhanging beam. For your exercise, Ajahn asking you to do this type of three types of beam: overhanging beam, and then primary beam, and then simple supported beam. Now, when you consider the one of this, you may start, this is going to be the pin, and this is going to be the roller, the support of the beam. They are different. What the different pin may have the horizontal force and vertical force. For this one, let me set this one A and this one B. For this one, you will have B sub X and B sub Y. Over here, you will have only A sub Y. Then, the first step, draw the free body diagram of the beam, and then determine the reaction at the support. That's why you got to specify the type of the support properly. Now, when you have this one, you got to take the beam out of the support and then set up. This is going to be the x-axis. Under the application of 6 kilonewton over here, the support as roller will have the reaction only for A sub Y. And then the support at the B, you got to have this one B sub X and this one B sub Y. It is very important to know pin has two reactions, B sub X and B sub Y. Roller have only one reaction. Now, since you need to take the moment, then you got to specify the length. This is going to be 3 meters. This is going to be 6 meters. So, basis upon A. Now, you get the proper free body diagram of the beam. Then, you have three equations. Summation of x sub x equal to 0, summation of f sub y 0 equal to 0, and summation of the moment equal to 0. You got to select one of these equations. Which one we going to use first? Okay, most of the time we gonna use this equation and take the moment at the point of maximum unknown. So summation of the moment about B equal to 0. If you take the moment about this one, you will see A sub y gonna rotate clockwise. So clockwise rotation gonna be positive. We have A sub y. Then the moment arm of A sub y gonna be 9 meter. That's gonna be in clockwise direction. 6 kilonewton gonna rotate in the opposite counterclockwise direction. So minus, and then 6 kilonewton. And the moment arm is gonna be 6 meter, and then set it up to be 0. You guys will have this one A sub y equal to, this is 36, and then it's gonna divide it by 9. Okay, then 40. This is 6 times 6 is 36, right? Okay, and then you got to be able, oh, I can forget one thing. I can forget what? 9 kilonewton meter. Soอาจารย์ cannot just summation it to be 0. You got to be very careful. You have this one 9 kilonewton meter. Okay. The incomplete free body diagram will cause you the problem. Okay. So you have 9 kilonewton in this counterclockwise direction. So this one you got to get it to be minus 9 kilonewton. Just take this one. My eraser just gone. This one. Okay. This one minus is going to be minus in opposite direction. Minus 9 equal to 0. So A sub y gonna be 36 plus 9, and then divided by 9. So it's going to be equal to 45 divided by 9. That's going to be 5 kilonewton. So you have this A sub y equal to 5 kilonewton. Then you have summation f sub x equal to 0. You can see you will have b sub x equal to 0, even though you set this one positive. And then the last one, summation of f sub y equal to 0 upward positive. You have b sub y, and you have this one a sub y plus 5, and this one minus 6 equal to 0. So b sub y is going to be equal to 6 minus 5, going to be 1 kilonewton. Okay, this is going to be 1 kilonewton. And then you get 2 points. Very simple. Get 2 points. Now, we're going to determine what? Determine the internal shear force. Bending moment occur at the beam as the function of the coordinate x. Okay, and the x gonna be from the left to the right. As I tell you, this is gonna be x meter. The problem is the beam separate into 2 segments. One is going to be this segment, okay, from A to 6 kilonewton. And then you have another segment from 6 kilonewton up until this one. Okay, so you got to set up your reference x-axis. If you said, then this is going to be x1. Okay, x1, the coordinate for B, coordinate from AB, from A to C. Set up the coordinate of the beam of the beam segment. We have two segments, so we have two coordinates. One is going to be from A to C. From A to C, it's gonna be what? X gonna start from here. Gonna start from here, and then move along this one. 1 meter, 2 meter, and 3 meter. So 0 less than equal to x1 and x1 less than equal to 3 meter, not equal, just before 6 kilonewton. Okay, then you have another one called x2. Just step up this for x2. X2 gonna be from C to B, and that's gonna follow the orange. That's gonna follow what? Since you have the first portion already, 0 from 3. So now x2 gonna start from 3 meter. 3 meter. This is 0, 1, 2, 3. And then 4, 5, 6, 7, 8, and then 9. You're going to start from 3 less than equal to less than it's less than equal to x2, and x2 less than equal to 9 meter. That's going to be your orange portion. Okay, this is going to be the symbol for your understanding, and this one gonna be from 0 up until close to 6 kilonewton. Okay, that's why it won't have equal. Okay, before, and then you got to start the second one. You got to draw free body diagram of the segment We have two segments, A, C, and C, B. Okay, let me cut this one over here. Then put this one on the diagram here. We will have the first portion. This is for the yellow portion, and the yellow portion corresponding to this x1 coordinate. And then we have the first A sub y x over here for 5 kilonewton. Then the free body cannot hold like this one. Okay, you got to have the sign convention. This is the sign convention of positive moment, and this is going to be the sign convention of the shear, and this is going to be the sign convention of the normal force. All of them is the function of the coordinate x1. All of them going to be the function of the coordinate x1. Then the internal forces and moment gonna make the segment to be in equilibrium. Then, following this one, we consider the body diagram of AC. Okay, and then summation of f sub y gonna be equal to 0. Then you can move up. Then this one diagram positive, we have u sub x1 diagram minus 5 kilonewton equal to 0. Then the function of the shear force going to be equal to 5 kilonewton. This is going to be for the first portion. Then if you take summation of the moment equal to 0 at the cut, okay, and then the m sub x1 gonna be positive, m sub x1 rotate in this direction. The 5 kilonewton has x1 moving arm rotate in opposite minus 5 x1, and then equal to 0. So m sub x1 is gonna be 5x1, and it's gonna be in kilonewton meter. This is the equation for the first portion. Okay. Now you have another portion. You just cut it again over here. Now you be gonna separate into portion one. You already finished the calculation from A to C, and then at C we have the force of 6 kilonewton. This is C. This is A. And at the point A, we have this one for 5 kilonewton. Now, X2 is going to measure from here to here. This is X2. But X2 only from 3 to 9 kilometer. Now, the member cannot be free like this one. It must be in equilibrium. To be in equilibrium, this one going to be m sub x2, prevent the rotation. And then this one, v sub x2, this one prevents the vertical displacement. This one gonna prevent m sub x2, horizontal movement. Now, okay, in this previous one, if you do summation of x sub x equal to 0, there is no horizontal force. The same, if you use f sub x equal to 0 here, m sub x2 going to be 0. Since the axial force always 0, we don't need to draw what so-called normal force diagram. You don't need to, because all of the normal force, they are 0. You don't need to write this one. Only shear force diagram and the bending moment diagram are important. Then, for the second portion, we consider the body diagram of the x2 coordinate. Let me put this one, x2 coordinate. This one free body diagram of the x1 coordinate. Now, basis upon this one, do the same thing. Summation of f sub y equal to 0, downward positive. So, v sub x2 downward plus 6 downward minus 5 upward, and then they are equal to 0. So v sub x2 gonna be 5 minus 6 equal to minus 1 kilonewton. This is gonna be the shear force v sub x2. Now, following this one, you take moment again here. Okay, this moment gonna make the counterclockwise to be positive. So this is m sub x2 in this direction. Then 6 kilonewton rotate in the same direction plus 6. The moment arm between 6 kilonewton and this section. You know, this is 3 meter. This is 3 meter. So the moment of the over here gonna be x2 minus 3. The moment arm. Okay, plus this one x2 minus 3 in the same positive rotation. This one gonna be in the opposite direction, minus 5, and then x2, and you put it equal to 0. Now, m sub x2 gonna equal to this one, 5x2, and then minus 6 times x2 minus 3. So this is gonna be 5x2 minus 6x2 negative to be positive 18. Okay, and then this one will eliminate each other. So m sub x2 gonna be minus x2 plus 18 kilonewton meter. Now you got the equation. Okay, you got the equation. You got to do what? You got to draw the table. Okay, that's gonna be x. Okay, and then you have v sub x and then m sub x. And then basis upon this one, you have x to be separated into two portions. Let me take you over here to portion. One will refer to x1. Another one will refer to x2. Okay. Let I can put this one. That's gonna be 1, 2, 3. That's for x1. And then for the x2, 3, 4, 5, 6, 7, 8, 9. Okay, you separate them into two portions. And then basis upon A to C, you have this equation from A to C. You can see V sub x1. Okay, this is going to be for x1, and this is going to be for x2. This is only x1. You can see V sub x1 is a constant, so this is going to be 5. Okay, even though it's start with 0, gonna be 5, 1, 5, 2 meter, 5, 3 meter, 5, 5 constant. Okay, no matter x1 is, they are constant. Now, for the second equation, m sub x1, this is gonna be 5. When this one is 0, 5 times 0 is 0. 5 times 1 is 5. 5 times 2 is 10. 5 times 3 is going to be 15. This is going to be kilonewton meter. This is going to be shear force kilonewton. Now, we have the second portion, V sub x2. No matter x2 is from 3 to 9, the value of v going to be minus 1. So this is going to be minus 1, 3, 4, minus 1, 5, minus 1, 6, minus 1, 7, minus 1, 8, minus 1, 9, minus 1. All constant. Okay. Now, let me move to this one. This one. Okay. This m sub x is minus x2. Is for this region. You start with minus 3 plus 18. Minus 3. Minus 3 plus 18 is what? It's going to be 15. Right? And then come to this one. Minus 4. Minus 4 plus 18 is going to be 14. Okay, minus 5 plus this one, minus 5 is going to be 13. Minus 6 plus 18, 12. Minus 7 plus 18, 11. Minus 8 plus 18, 10. Minus 9 plus 18, this one going to be 9. Now, you get all the number and you are ready to draw your shear diagram. Okay. On the shear diagram, this is x meter, and this is going to be V. And in kilonewton, this is in kilonewton. Now, basis upon what we have here, we start from this one, 0, 2, okay, and then we have this one, 0, 1, 2, 3. And then we have 3. So starting here, 3. Okay. 4, 5, 6, 7, 8, and then 9. 4, 5, 6, 7, 8, and 9. You see coordinate, right? The blue and the red. Then the value of this one is 555. 0 is 5, 2, 5, 3, 5. So all of the value is a constant. You have this one to be plus 5 and then plus 5. And then for the rest of this one, it's going to be minus 1. Let me put it to be larger than this one, to be 10 millimeter. It's going to be, this is okay. And this is going to be only 1 millimeter. So this is going to be minus 1 and minus 1. So you will have this one going to be shear diagram. And this shear diagram has Vmax equal to 5 kilonewton. Okay. You put the scale, 1 millimeter per 1 kilonewton. You have positive up here, negative to be down here. Then for the bending moment, let me put it over here. Here, this is x meter. Do the same thing. Just put this one over here. And then you have this one moment in kilonewton meter. And this is gonna be 0. And then start 1, 2, and 3. And then you have this one, 3, close to each other on the side. And then 4, 5, 6, 7, 8, and then 9. Now, you have to cut it, okay? Hopefully, let me put the scale, okay? Put the scale, 1 kilonewton meter per 1 millimeter. Now, you have this one 0. So we start 0 is 0. 1 gonna be 5. Okay, that's gonna be 5 millimeter. And then next 10. That's gonna be 10 millimeter. And then 15. We have this one for the 15. If you plot the graph, you can see the graph is going to be like this one. Okay, and this is going to be 5, 10, and this one 15. Now, on the opposite sides of underside below of this table, we start with 15. So we start here with 15. And then 4, 5, 6, 7, 8, 9. 4 is going to be 14. This one, 14. And then next, 13. This one, 13. And 12. We have this one, 12. And then 11. And then 10. And then 9. If you plot the graph, you will get this one to be linear. And then 14, 13, 12, 11, 10, and this one 9. This is going to be your moment diagram. This is going to be M diagram. Okay, and then we have Mx to be 15 over here. Both blue and red, 15 kilonewton meter. This is one of an example. Okay, you guys can do it. Okay, now I will take the picture and show you. Let me move to the next one. This one again called simply support the beam. Many people just call it simple beam. Okay, some people just call it just simple beam. Full name, nickname, simple beam. Simply support the beam. No, let me move to the next one. Okay, next one over here. You may go back and try to do it by yourself because we have limited time. Okay, now let me move to this one. This is a cantilever beam. Okay, the cantilever beam different from simple beam. This lower, this beam. This one we have the support. This one to be quick support. Okay, over here it's gonna be quick support, and over here this one gonna be free end. Okay, different from this one, lower and pin. This one gonna be fixed and free. Let me move you to the next problem. On this problem again, it's subjected to uniformly distributed load. Also, the building 1,350 kilonewton meter and the point load. This problem, the beam subjected to three types of importance of loading. Uniformly distributed load of 60 kilonewton meter and the moment M equal to 1,350 kilonewton meter and the point load. You may call it F. Some people may call it P. Whatsoever is going to be 265 kilonewton. The problem asks you the same question. You got to the free body diagram of the beam and then determine the reaction and the support. The question already standard. Okay. And then later asks you to determine the internal force and bending moment occur for a function of x1 and x2. Again, how come is specify x1 and x2? Because the beam can separate into two portions. This is first portion subjected to uniformly distributed load. And then another portion there is no distributed load, only has the point load and bending moment and the free end. Okay, now we got to start by drawing the free body diagram of the beam. Okay, since this beam subjected to the uniformly distributed load, this is going to be 60 kilonewton per meter, and then this is point load up to 65 kilonewton, and this is going to be 1,350 kilonewton meter. Okay, then free end has no reaction, it's free. Okay, that's the fixed end gonna have this force to prevent it for vertical movement. Let's put this one A. Okay, put this one B. Put this one C. It will be A sub Y. And then for the X, we're gonna have this one to be A sub X. And this one, you got to have this one to be A sub A. Okay. Now, following A, you may do the summation of x sub x equal to 0 A sub x in this direction to be 0. Very simple. Okay. And then you do the summation of f sub y equal to 0. Again, how come you will take moment first? You can take the moment if you prefer, it's up to you. But most of the time, we take the moment equal to 0. Take this direction to be positive. Why? Because the leg rotate clockwise. So this one must rotate again counterclockwise. Okay, so we have M sub A rotate in this direction. Then we have minus 350 kilonewton. Okay, it's already removed. And then we have 265. That's why you got to put that direction, the length of the segment of the beam. Okay, the total is 6 meters. This is 4 meters. This is 2 meters. This is 4. Therefore, this is going to be 6 minus 4. This is going to be 6 minus 4 equal to 2 meters. Okay, 2 meters. No, for this one, 6 kilonewton has 6 to 65 kilonewton has 6 meter moving arm rotate in the opposite direction minus 6 meter times to 65 kilonewton. And then you have this one, you have this one, you have this one. Okay, this is going to be 60 kilonewton per meter times 4 meter. Okay, the resultant force cut going to be what? 240 kilonewton. And at what? At the middle of this one, this is going to be 2 meter, half of 4 meter. Then it's rotated opposite to M sub A, minus 240 kilonewton times 2 meter, and then that's gonna be 0. So M sub A gonna have this one to be 3,420 kilonewton meter in this direction, counterclockwise direction. And then for summation of f sub y equal to 0, this one is upward. Okay, so a sub y, this one negative, minus 240. This one minus 265. The moment we need to consider it, okay, only consider the force equal to 0. So A sub y gonna be 505 kilonewton. So this is gonna be 505 kilonewton. A sub x gonna be 0. M sub A gonna be 3,420 kilonewton meter. Okay, now the beam separate into 2 portions, and you can see there may have many reference if you like to use x1, x2, x3, and x4. Okay, basis upon this one is up to you. They are different. X1 from here to here. X2, what's X2? X2 supposed to be actually come up until here. And X3 start from here to here. Okay, I may review what we have it for the code. You may select many times. This is going to be your X1. Okay, this is going to be your X1. And then this is can be your X3. Okay, and then this is can be your, this is passing this one, can be your X2. Okay, and this one can be the X4. In our consideration, we don't use this type we use it from the left to the right in this direction. Okay, and then for this one, you will see x start from A to B. Okay, start from A to B. So x1 start at this point when x equal to 0. And then it's move along this one up until this one, x equal to 4 meter. So for x1, you got to break it from 0 less than equal to x1. x1 less than 4 meter. It's going to be something like this one. Okay. How about x2? Again, x2, you start from here. But since here to here already used, so x2 gonna start from this point. Okay, from this point. So for this one, x2 gonna start from here. From here. And this is what? This is 4 meter. 4 less than equal to x2. x2 less than over here. This is 6 meter. Okay, this is going to be for x2. Now, how about x3? x3 start from here. Okay, and from here to here. x3 start from what? From 4 meter less than equal to x3. And then x3 extend up until less than 6 meter. You can see they are not the same. x1, x2, x3. Okay, again, we start from the left to the right. Most of the time, we prefer to use this x1 for this yellow. And we will select this x2 for the green. Okay, for the green. The x3, sometimes people use it, but most of the time, I can prefer to use x1 and x2. If we decide to use x1 and x2, what we have, we got to cut this portion and this portion. And this portion is going to be for the coordinate x1. Okay, and then for the answer portion, this one going to be for coordinate x2, the green. Now, you may need to draw this one. Okay, this is going to be 60 kilonewton per meter. And then this is going to be your x1. Okay, and then the end of this one subjected to 505 kilonewton shear force, and M sub A, that's gonna be 3,420 kilonewton meter. And then the internal section will have internal forces and moment. So that's going to be M sub x1. And side convention, this is going to be V sub x1. And this is going to be N sub x1. And then, since you know, summation of x sub x to be 0, no horizontal force. So, N normal force for the x1 going to be 0. Okay. Now, for the second one, you do the same thing. This is going to be your 60 kilonewton per meter. Now, we have this one for our x2. But our x2 goes start from 4 to 6. Okay. That's gonna be the coordinate of this one. And again, this is gonna be 505 kilonewton, and the moment here 3,420 kilonewton meter. Again, the section here gonna have the moment m sub x2, and this one gonna be v sub x2, and for this one n sub x2, summation of x sub x equal to 0, n sub x2 gonna be 0. Now, you finish drawing the free body diagram for x1 and x2. Okay, you got to again start consider the free body diagram of the segment basis on x1. That's going to be this one. Okay, take this one, eliminate it. Just consider that one. You can move. Okay, you may have what summation of the f sub y equal to 0 if you prefer. You just take that one to be positive. That's going to be v sub x1 downward. The certain force here, gonna be 60 times x1. This is gonna be 60 times x1. The distance half over here, x1 over 2. If you take this one downward, this one plus 60 x1 downward, 505 upward, minus 505, and then equal to 0. V sub x1 gonna be equal to 505 minus 60 x1 kilonewton. That's gonna be the equation for the transfer shear. Okay, now summation of the moment, okay, equal to 0. Take the moment over here, eliminate v sub x1. Take the moment here, n sub x1 in this direction to be positive. Okay, then 60 x1 has half of this one, x1 over 2 in the same direction, plus 60 x1, okay, and time this one, x1 over 2 in this direction. Then 3,420 located in the same direction. However, minus 505 times x1, and then that's gonna be equal to 0. Now, n sub x1, this one gonna be equal to 505 x1 positive, and this one gonna be negative 3,420. This one gonna be negative 30 times x1 square in kilonewton meter, and that is going to be for our first portion, and then we consider again the free body diagram of the segment. This is going to be of x2. Okay, this is going to be basis on this one. Then do the same thing. Summation of f sub y equal to 0. Downward, positive, v sub x2 downward. And then this is going to be the total area. Okay, 60 times 4. 240 kilonewton at half of 4 meter. So it's gonna act 2 meter and 2 meter, half of the 4 meter. Okay, now this downward has 240, and then this one 505 upward minus 505, and then take it to be 0. V sub x2 gonna be 505 minus 240 is gonna be 265 kilonewton. It's gonna be a constant. Gonna be a constant. Be a constant. Then we have the last one, summation of the moment here to be 0. This counterclockwise is positive m sub x2. M sub x2 take moment over here. Then you can see 240 gonna rotate in the same direction plus 240. This one is tough. It's tough. This one is tough. What's going to be the length from here to here? Okay. What will be the length from here to here? Ajahn should say all of this is x2. Okay. This is 2 meter. So the distance that we are looking for, the orange. Okay. What can be the orange? It's going to be x2 minus 2. So this is going to be x2 minus 2. The distance from here to here, that's going to be x2 minus 2. That's going to be x2 and then minus 2. Now, T420 rotate in the same direction of m sub x plus 3420. Then 505 in the opposite direction minus 505. Moment arm gonna be x2. That's gonna be x2. And then put everything to be 0. We have m sub x2. This is equal to 505 x2 positive minus 3420, and then this one minus 240 times x2 minus 2. Okay, and this one when we count it, this one minus 240 x2 minus plus 480. That's going to be for this term. Then this one and this one 505 minus 240 x2. You got to get this one 505 minus 265 x2. Then minus 3420 minus plus 480. So you should have this one minus this one plus this one minus 2940. So this is going to be m sub x2 in kilonewton meter. Okay. Then after you get the equation, please understand it. Okay, this one is going to be for x1. This one is for x1. And again, this one is for x1. And for the x2, 4 to 6, this one for x2. This one is for x2. Now do the same thing. you got to put this one x v sub 8 kilonewton sub 8 kilonewton meter. Then we just draw the table. We just draw the table as we did before, and then x separate into two sets. Okay, again, x separate into two sets from 0 to 4. That's 0, 1, 2, 3, and 4. This is going to be first portion. And then 4 to 6. Okay, 4 to 6. We do it again. 4 to 6. 4, 5, and then 6. Okay, 4, 5, and then 6. You may cut this one. And then you may see this one is for x1. This one is for x1. And this one is for x2. And you know, the x1 going to be the yellow. And the x2 going to be the green. Now, coming over here. When you have 0, when this one is 0, this one going to be 5 or 5. Okay. And this one is 1. 5 or 5 minus 60. Okay, you got to get this one. 4, 4, 5. And then this 5 or 5 minus 60 times 2. 60 times 2 is 120. Okay, 5 or 5 minus 120 to 85. Then 3, 5 or 5 minus this 1 times 3, 180. 180. You got to have this one. 325. For 4 minus another 60. That's going to be 265. Okay. Now, coming into this equation, when x is 0, when x1 is 0, this is going to be minus 3,420. If you put 1, this is going to be 505 minus 320 minus 30 times 1. You got to get minus 2,035 minus 2,530. And then put 3 for x1. You got minus 2,075. Put 4. You got minus 1880. Okay, 1880. Now, move to the green. The green over here. And then out of the x2 is, that's going to be 265, 265, and 265. And then for this one is going to be 4 times 240 plus 480. M sub x2 is going to be this term. Okay. And then, sorry, it's going to be this equation. Put 4 over here. Okay. 265 times 4 minus 2,940 got the same number. I should note that at the same location, you guys are supposed to get the same number, except that is the point load over there, or the moment over there. Okay, please check. But you got to do the same for, because it's going to be the end. This is going to be the starting point. So you got to consider both. Then put the 5 over there. Okay, you got minus 1615. Put the 6 over here. You got minus 1350. Now, come to the shear diagram. Come to the shear diagram. This is going to be your X meter, and then you start from here. That's going to be kilonewton, and then this is 0, this is 2, this is 4, this is 6. Okay, now you got to put a hotter scale. Okay, the largest is going to be 505. Let's put scale 500 kilonewton for 20 millimeter. So we will have this one around 20. That's going to be about here, 505. And then 385. Okay, going to be 2 times of this one. It's going to be tough. Let me put scale 500 for 10 millimeter. That's going to be easier. 500 from 10. This is going to be 505. Okay. And then for this one, okay, you should get it. This one, linear. It's linear. That's going to be 265. That's going to be about 6 millimeter. This is 265, and it's going to be linear. Okay, since the function is linear, that's going to be 385. If you prefer to put on this one, 445, and this is going to be 3 meter, 325. This is 1. Then the rest of this one, 265, just put this one. If you put 4, 5, 265, and 265, okay, this is going to be the shear diagram. And then we max equal to 505 kilonewton. Okay. Now, take another one before I take a break on this one. For the moment diagram, let Ajahn put this one over here, and then for this one, I think they are all negative. Okay, so I can put it over here. They are all negative. Most of it gonna be m in kilonewton over here, and that's gonna be 2, 4, 5, and then 6, and this is gonna be x meter. Now, at x equal to 0, okay, 3, 4, 20, 34, 34 is gonna be 34 millimeter. We put scale 1000 kilonewton meter per 10 millimeter, so 3.4. Okay, and then this is gonna be 2.5. This is gonna be 2.5. This is gonna be 2.9. This is gonna be 2.9, and this is gonna be 3 meter. 2.2, 2.2, and this is 1.9 about this one. And you can see when you plot it, this is gonna be curve. This is gonna be a curve. Then here you get the same 1850. Okay, and over here 1880, 1880. Okay, they are the same. And then 1615, 1.6, okay. This one 1615 minus, and then minus T for 20. This one minus 2945 minus 2530 minus 2175. And then this is linear. You see the function is linear. So you may draw this one for a linear line. And then over here, you get 1350. And this is going to be your moment diagram. And then max gonna be minus 3420 kilonewton meter. That's gonna be your shear diagram, moment diagram. Okay. Anyway, since you guys in polymer engineering, civil engineering, this one should be a must because the cost of mechanics of material, you're going to use it again. Okay, like next lecture of the mechanics of material, Ajahn will lecture how to draw the shear diagram and moment diagram. Okay, let us take a 5-minute break before we have another example to finish the class. Okay, class, let me take you to the second part of our 17th lecture, and we have finished this example already. Okay, and Ajahn should go through it again to mention about something important. First, drawing the free body diagram are very important. Both the free body diagram of the beam for determining the reaction and later free body diagram of the beam segment. After you guys draw it, recall I did a mistake to forget about the moment 9 kilonewton meter. So don't repeat my mistake. Then after you get all of the reaction, you may get 2 or 3 points. Okay, you should get 2 or 3 points. That's more than enough to pass this one correctly. Then you got to consider, since the beam separate into 2 portions, you got to select the coordinate x1 and coordinate x2. And you got to know that coordinate for x1 start from the left to the right. Our x-axis is like this one. This is 0 meter. This is 3 meter. This is 9 meter. Following the reference x coordinate. Now, x1 going to start from 0 to 3. Okay, 0 to 3. When you start from 0 to 3, you use up of this one. Then, for the x2 going to start from 3, 4, 5, 6, 7, 8, and 9. That means this portion is for x2, and then 3 less than equal to x2, x2 less than 9 meter. Okay, and then for x1, 0 less than equal to x1, x1 less than 3 meter. These are very important. Then you cut your beam into segment. You write the equation for the shear force and the bending moment. And Ajahn should say, typically, for this step, you don't need to use the moment equation first. And Ajahn would like you to use summation of f sub y equal to 0 and summation of the moment equal to 0. And Ajahn should say something. If you do the dm by dx, you diff x1. This is x1. You did 5x1 over dx1. You get this one to be 5. And 5 is going to be the shear force. So this is important to know that dm by dx gonna be shear force. This is going to be slope of m diagram equal to the shear force. You draw the moment diagram, you take a look at the shear force. And then following what we did, you got to draw the table correctly. And again, when you draw the table, for this example, the point at 3 meter subjected to the force of 6, then this is 5, this is -1. So this equal to the 6 kilonewton applied force. Again, if you noted of this one, this is 5 kilonewton. This is equal to reaction at this point. And this is going to be 1 equal to reaction at that point. Okay, now draw the moment diagram. You will have this one. Again, if you draw this one, the slope over here, 15 divided by 3, you will have slope over here, 15 divided by 3 equal to 5. Again, you have dm by dx equal to the slope. 5 is what? 5 is shear. So dm by dx equal to v. Okay, and the same thing over here. Slope over here. Okay, slope over here. You can have it dm by dx, and then this is diff of x2, diff of s3 minus x2 by dx2. You have 0 and then -1. This is -1 equal to the shear force. Then, in conclusion, okay, dm by dx equal to v. And sorry for this one. It should be in English, but this one is what it said. If the point load downward, the shear diagram gonna be decreased. Or I should say, if the force is downward, delta V negative. Again, if the force is upward, the change of shear gonna be positive. Okay, this is going to be showing over here for the downward force that Ajahn just mentioned about it. And then the moment, this one, sorry, in Thai, the moment over here is going to be 9 kilonewton meter. And then the moment that's rotate counterclockwise, delta m going to be negative. And then for the clockwise moment, delta m going to be positive. Okay, all of these relationships are important to check the result of your shear force diagram and bending moment diagram. Now, let us move you to the next example. This one is the beam subjected to uniformly distributed load of 50 kilonewton. Then this is roller. This is pin. So pin has Cx, Cy. A has only A sub y. And then the C sub x, summation of F sub x equal to 0. C sub x gonna be 0. Then take the moment about A. Since C sub x is only 0. So C sub x gonna time this one 8 meter, rotate in this positive direction 8. C sub y, sorry, SC sub y. And this gonna have the resultant force equal to the area. That's gonna be 50 kilonewton per meter times 8 meter. Sorry. You're gonna have this one meter, half meter, this is 400 kilonewton. And the distance from here to here is gonna be 4 meter. So the 400 gonna time 4 in this negative direction, counterclockwise. And our sorry for this one, in wrong direction. It's gonna be in this direction. Gonna be in this direction. Then C sub y gonna rotate in the positive direction. So C sub y times 8, you get 200 kilonewton. Summation of F sub y equal to 0. Then we should get A sub y plus C sub y equal to 400. Then C sub y is 200. So put C sub y over here. You get A sub y to be 200. And again, should say this kind of beam used a lot in civil engineering, such as the precast RC beam or precast pre-stressed concrete beam. And I should mention, due to the symmetric uniformly distributed load, we have A sub y equal to C sub y equal to 200 kilonewton. And then this beam is easy because when you move along x-axis, there is no change of the loading. The uniformly distributed load always 50 kilonewton per meter constant. Then in this problem, you have only one coordinate from point A up until point C. So if you set this one to be x, you will have this one from 0 to 8 meter. So 0 less than equal to x, x less than equal to, actually only less than, not equal, x 0 less than x, x less than 8 meter. Now you put the applied load of 50 kilonewton meter with this reference x-axis, okay, and then the portion or the segment of the beam must be in equilibrium. We have the shear force and the bending moment. We don't have axial force because summation of x sub x equal to 0, n gonna be 0. Now, still the coordinate 0 less than x, x less than 8 meter. Okay, just start from here up until here. Actually, you should not have this one for equal. Then you have summation of f sub y equal to 0. Downward gonna be positive. So V is downward. Then minus 200 opposite direction. And this one, you will have the area 50 times x1 in positive direction. 50 times x, then equal to 0. When you rearrange it, it's going to be 200 minus 50x. And then for the moment, take the moment at this point, and then you will have what? You will have the moment clockwise to be positive. If you set moment counterclockwise to be positive, you will have m. Okay, then the distance from here to here going to be x over 2. So rotate in the same direction plus 50x times x over 2. and then 200 gonna time the distance from here to here. That's gonna be x. Rotate in opposite direction minus 200. Sorry, should put it in red. Minus 200 x equal to 0. Then m gonna be 200x minus 50x times x over 2. You get this equation. Now, you come to the table. You plot the shear force. That's going to be in kilonewton. And the moment, the value of x from 0, 1, 2, 3, 4, 5, 6, 7, 8 into the equation for the shear. Okay, and for the moment. And then when you plot the graph, you will get the graph like this one. And Ajahn should mention one thing for uniform load. For uniform load, you have what? For W is a constant. You will have shear in the linear equation. So the linear gonna show the diagram in the linear manner. And then for the M over here, the equation for the M over here is going to be second order polynomial equation. Since it is the second order polynomial equation, the graph of the moment gonna be curve. Okay, graph the moment be curve. Please remember it. Okay, and then following this one, you have dv by dx equal to minus w. You may do this one. Dv of 200 minus 50x by dx. You will have div of 200 by dx minus div of 50x by dx. You have this one. 0 minus 50 is going to be minus 50. Minus 50 is going to be minus W, 50 kilonewton per meter. Then dm by dx, as Ajahn showed you from the previous example, the slope of the moment diagram going to be the value of shear. The slope of the shear diagram going to be minus the value of distributed load. And then the point load, point load over here, okay, I should say delta V positive when we have the force upward. The same over here. The same over here also. We have this one for C sub Y. We have this one for C sub Y for 200. We have F upward, delta V positive. And we have one more thing. The point over here has 0 shear. This is what? This is the point of dm by dx equal V equal to 0. So maximum moment occur when shear force equal to 0. Let me skip this one in Thai. Okay. And then we have more example and we run out of time. I got to ask you to study it by yourself. Anyway, since shear diagram and moment diagram are very important, and Ajahn would like you guys to get score from problem number 3. Ajahn will be back with two more important example. And I hope Ajahn already provide you all the extra example. Please go back and try to review it by yourself. By the meantime, any question? No question? Okay, thank you very much. See you again on Wednesday.